Welcome to Everything Explained. I'm your host, and today we're diving into quantum encryption and why it's one of the most talked about ideas in modern security. It sounds like science fiction, but a lot of it is already real, and it's changing how we think about keeping secrets. What is quantum encryption? In its practical form, quantum encryption is a way to share a secret key between two people using the rules of quantum physics. The name you hear most is quantum key distribution, or QKD. Think of it as a way to hand over a key to a lock, but with a guarantee baked in by the laws of physics. If anyone tries to listen in, the key changes in a detectable way. Once both sides have a clean key, they can use a standard cipher to encrypt messages. Here's a simple picture of how it works. Imagine Alice wants to send Bob a key. She sends photons, tiny particles of light, one by one. Each photon is prepared in a random way, like choosing a random color or a random orientation. Bob doesn't know what Alice sent until he measures each photon, and he also does so with a random basis. Think of it as choosing a random method to read the photon's state. After many photons, they compare which basis they used over a public channel. Every time they use the same basis, that measurement becomes a candidate bit in the key. They discard the rest. After this sifting, they have a raw key. But there's a crucial twist. Some of the photons are sent to test whether anyone was listening. They sacrifice a portion of their data to estimate the error rate, the fraction of bits that don't match what Bob should have if no one was tampering. If the error rate is too high, it's a sign that an eavesdropper, often called Eve, has tried to intercept the transmission. In that case, they abort and start over. If the error rate is acceptable, they apply error correction and privacy amplification to produce a shorter but provably secure key. The math says you can generate a key that is secure even if the attacker has unlimited computing power, and any attempt to do better would introduce more errors and get detected. Why is it so secure? There are two big physics ideas at work. First is the no-cloning theorem. You cannot make a perfect copy of an unknown quantum state. If Eve tries to copy the photons to measure them later, she inevitably disturbs the original photons. Second is the uncertainty principle. Certain properties of a quantum system can't be known exactly at the same time. If Eve tries to measure one property to learn the key, she ruins information about the other property, and that shows up as errors. Together, these rules mean that the act of eavesdropping leaves a telltale trace. There are also security proofs behind QKD. In idealized models, the math shows you can generate a key that is secure even if the attacker has unlimited computing power. In practice, engineers add defenses against real-world tricks, like the photon number splitting attack, where the source sometimes sends two photons at once. Techniques like decoy state protocols help defeat that. Some researchers are pursuing device-independent QKD, which tries to guarantee security even if your devices are imperfect or even partly controlled by an attacker. It's exciting, but still challenging and expensive in the real world. How does quantum encryption fit into the real world? Right now it's most often used to secure the key itself, not every message. A common setup is to use QKD to distribute fresh keys on demand, and then encrypt messages with a fast classical cipher using those keys. In practice, that gives you much stronger security for the key exchange, and the messages benefit from it. You can also hear about a one-time pad, which is theoretically unbreakable if you have a key as long as the message and used only once. QKD can help you generate that perfect key, but you still need perfectly random keys and careful implementation. Distance and practicality are the big hurdles. Quantum signals are delicate. They travel best over short fiber links or through the air, and they suffer loss as they travel. That limits how far you can go before you'd need repeaters, and quantum repeaters are still more future promise than today's reality. Weather, temperature, detectors' accuracy, and even the quality of the light source matter. Researchers are making progress with satellite-based QKD, which can leap over continents, and with metropolitan fiber networks that connect city centers. You've probably heard big demonstrations from satellites and from lab-to-lab fiber links in Europe and Asia, showing that the basic idea works at scale. It's also worth noting what quantum encryption is not. It's not a magical replacement for all classical security. If someone steals your key storage or tamper with the hardware, that can break security too. And there are other quantum-secure approaches outside QKD, like post-quantum cryptography, which aims to harden ordinary encryption against quantum attacks. The best posture today is a layered defense. Use quantum-safe key exchange where possible, and keep monitoring and improving the whole system. So, why does this matter? Because in a world where computers get faster and new breakthroughs come faster, a future adversary could crack today's codes with enough power. Quantum encryption doesn't just make somebody work harder to break in. It gives you a built-in alarm and a way to lock your secrets with schemes that physics itself makes trustworthy. In the end, quantum encryption is not magic. It's a precise, physics-backed way to share keys so that any eavesdropping shows up immediately. And that idea is powerful enough to change how we think about securing communications in the years ahead. Thank you for listening to Everything Explained. Until next time, keep curious, stay skeptical, and remember, the universe doesn't just tell us secrets, sometimes it hands us the tools to protect them. So stay curious, stay calm, and trust the physics that guards your secrets.